A group of physicists just published something that made the entire scientific community stop and pay attention. They didn't just theorize about breaking the light speed barrier. They proposed a framework, a real mathematical structure for how a spacecraft could travel not just at light speed, not twice light speed, but potentially thousands of times faster. And the craziest part? It doesn't violate a single law of Einstein's physics. This isn't science fiction anymore. This is peer-reviewed science, and it changes everything. Let's be brutally honest about where we stand right now. The fastest object humanity has ever launched is the Parker Solar Probe, clocking in at roughly 635,000 kilometers per hour. Sounds impressive until you realize that at that speed, reaching the nearest star, Proxima Centauri, would still take over 6,000 years. 6,000 years. That's longer than all of recorded human civilization. So when scientists say they found a potential pathway to faster-than-light travel, it's not just exciting, it's existential. It's the difference between humanity being permanently trapped in one tiny solar system and becoming a species that crosses galaxies. Einstein told us back in 1905 that nothing with mass can reach the speed of light. As you accelerate, your mass effectively increases, demanding more and more energy. To hit light speed, you'd need infinite energy. That's not a technical limitation. That's a wall built into the fabric of reality itself. And for over a century, physicists accepted that wall as unbreakable. But here's what most people miss. Einstein said you can't travel through space faster than light. He never said space itself can't move faster than light. And that loophole, that tiny crack in the cosmic rulebook, is where this entire breakthrough lies. Back in 1994, a Mexican physicist named Miguel Alcubierre asked a brilliant question. What if instead of pushing a ship through space, you moved space around the ship? He proposed a warp bubble, a region of space-time where space itself contracts in front of the vessel and expands behind it. The ship, inside the bubble, isn't technically moving at all. It's sitting still in its own local patch of space-time. But that patch is surfing across the universe at any speed you want. There's no speed limit for how fast space itself can stretch and compress. It already moves faster than light at the edges of the observable universe right now. That's not theory, that's measured fact. The problem with Alcubierre's original idea was devastating, though. It required something called negative energy, exotic matter with properties that, as far as we know, doesn't exist in nature. The amount needed was absurd. Early calculations suggested you'd need more energy than exists in the entire observable universe just to create one warp bubble. So the concept was brilliant, but completely impractical. A beautiful equation with no engine to power it. This is where things just changed. A team of researchers led by Dr. Eric Lentz at the University of Göttingen proposed a new class of warp drive solutions that eliminate the need for negative energy entirely. Let that sink in. No exotic matter, no impossible fuel source. The mathematics use what physicists call positive energy solitons, self-sustaining waves in space-time that can carry a bubble at superluminal speeds using only conventional energy sources. Now, conventional doesn't mean easy. The energy requirements are still enormous. We're talking about harnessing energy on a scale that humanity won't achieve for decades, maybe centuries. But the critical shift here is that we went from physically impossible to physically possible, but extremely difficult. That's not a small step. In the history of science, that kind of reclassification has preceded every major technological revolution. Picture it like this. Imagine you're standing on a conveyor belt that's moving forward. You're not walking, you're not running, you're standing completely still. But relative to someone watching from the side, you're moving. Now scale that up to the fabric of the universe itself. The proposed warp bubble would create a controlled distortion in space-time. In front of the ship, space compresses, pulling the destination closer. Behind the ship, space stretches, pushing the origin further away. The ship rides this wave of compressed and expanded space like a surfer riding an ocean wave. And because the ship itself is stationary within its bubble, the passengers inside would feel zero acceleration, no G-forces crushing your body, no time dilation tearing apart your biology. You step in, the bubble activates, and minutes later, you're orbiting a star that used to be centuries away. Multiple teams have since built on this work. Dr. Alexei Bobrik and Gianni Martiere published additional models showing that the shape and structure of the warp bubble can be optimized to reduce energy costs dramatically. Each new paper shaves off another impossible barrier. Each revision makes the numbers slightly less insane. Here's something most people don't realize. One of the biggest problems with conventional near-light speed travel isn't just the energy, it's time. Einstein's relativity tells us that the faster you move through space, the slower you move through time. If you somehow accelerated a ship to 99.9% of light speed and traveled to a star 50 light-years away, you might experience only a few years on board. But when you came back to Earth, everyone you knew would be dead. A century would have passed. You'd be a stranger in your own world. Warp travel potentially solves this nightmare. Because the ship isn't moving through space in the traditional sense, the extreme time dilation effects may not apply. The clock on the ship and the clock on Earth could theoretically stay synchronized. You could travel to distant stars and come home to the same world you left. That's not just a technological advantage. That's the difference between exploration and exile. Let's not pretend this is happening next year. The energy required, even with the optimized models, is still roughly equivalent to the mass energy of the planet Jupiter. We don't have anything remotely close to that capability. Our most powerful energy source, nuclear fusion, is still struggling to achieve sustained reactions here on Earth, let alone powering a space-time distortion engine. There are also deep questions about what happens at the boundary of the warp bubble. Some models suggest that particles accumulating at the front of the bubble would release catastrophic bursts of radiation when the bubble collapses. You'd arrive at your destination and immediately obliterate everything in front of you, not exactly a friendly greeting for whatever civilization you're visiting. And navigation is another unsolved puzzle. Inside the bubble, you're causally disconnected from the universe outside. You can't steer, you can't see where you're going. You'd have to pre-program the entire journey before activating the drive and hope nothing unexpected sits in your path. But here's what makes this moment genuinely historic. For the first time, we have peer-reviewed, mathematically consistent frameworks for faster-than-light travel that don't require fantasy physics. Real physicists at real institutions are publishing real papers, and the equations are holding up under scrutiny. DARPA, the same agency that helped create the internet, has funded research into advanced propulsion concepts. NASA's EagleWorks laboratory conducted experiments on space-time distortion, and while results were inconclusive, the fact that they're testing at all tells you something. The conversation has shifted from if to when and how. 200 years ago, the idea of humans flying through the air was considered madness. 100 years ago, breaking the sound barrier was called physically impossible. 50 years ago, landing on the moon was a fantasy. Every single time, someone found the loophole, the crack in the wall, that everyone else had accepted. Faster than light travel is the next wall. And for the first time in human history, scientists aren't just dreaming about what's on the other side. They're drawing the blueprints. The math works. The physics allows it. The only question left is whether we'll build the technology fast enough to use it. The stars have been waiting for us for 13 billion years. Maybe it's almost time we finally showed up. If this gave you chills, subscribe and hit that notification bell, because the future of space travel is unfolding right now, and you don't want to miss what comes next.